Hello, my name is Professor Richard Squitieri, and in this YouTube series, we will be navigating through the complexities of organic chemistry, and it will be paralleled to the presentation in a textbook written by Klein, 3rd edition. To begin with today, we're going to start with the basics of organic chemistry, bonding and molecular structure. For the most part, the first few chapters is going to be a review of the materials presented to you in general chemistry, and these materials will form the foundation that's needed for us to build and explore organic chemistry. So to start, what is organic chemistry and how does it relate to the other disciplines of chemistry? Organic chemistry is the study of carbon. Of all of the elements on the periodic table, we're going to be mainly focused on carbon in this course. We're going to be focusing on the electron flow of the reactions with carbon. Throughout the entire semester and year, I encourage you to really focus on this flow of electrons from negative to positive, creating new bonds and breaking bonds. Every reaction that we do will involve bonds being broken and bonds being formed, following these electrons from negative to positive to form these new bonds. The manipulation of molecules by both nature and humans to form new molecules is the primary importance of organic chemistry. Nature itself does organic reactions constantly in your body, in the environment. We're also able to do these reactions as humans in a laboratory setting, in, for example, a flask, where we're able to manipulate molecules, break bonds, and form bonds. Organic chemistry is all around us. There are many aspects of life, many different parts of life that rely on organic molecules that you might not really understand or appreciate now, but by the end of this course, you'll be very familiar with a lot of these molecules. For example, looking at this slide, we have in the top left Hot Ones, a popular TV series where celebrities taste different hot sauces with increasing amounts of heat. In the right picture, we have some coffee, and in the bottom left, we have oranges. The active component of many of these substances are organic small molecules. For example, in the top left, we have capsaicin. This molecule is found in peppers and chilies and hot sauces, and it's what gives that spicy flavor. This molecule will bind to receptors in your mouth, causing an electrical signal to go to your brain, which you experience as pain. Caffeine is the active component in coffees and teas and energy drinks that gives you that little zing. And other more therapeutic molecules, such as vitamin C or ascorbic acid, can be found in oranges. All three of these molecules share in common that they're built on an organic, carbon-based framework. In this course, we're going to be learning different ways to piece together these molecules from very small building blocks. This is akin to creating a structure with Legos or Connects from small pieces, building it into a larger and larger, more complex structure. Organic chemistry is all around us. You're familiar with many of these tastes and smells that are shown here, some of the organic molecules that show those properties. If something has a unique smell to it, what you're experiencing is one of these organic molecules binding to receptors in your nose that cause an electrical signal to your brain which triggers a memory for that specific smell. The same is true with taste, as discussed with the capsaicin example. A large amount of therapeutics are based on carbon-based small molecules. Polymerization reactions of these carbon-based molecules can lead to the production of plastics and rubbers. And most of the food that we eat is built of small organic molecules, carbon-based molecules. It's even present in the clothes that we wear. When we piece together these small molecules, we can build larger molecules or structures, macromolecules, and these large structures that are built of thousands of individual carbon atoms, oxygen, nitrogen atoms, build the macromolecules that our body uses to communicate and function. For example, one of the most common bonds used in biology is the peptide bond between a carboxylic acid and an amine to form an amide. This peptide bond is the most important bond in the building biological systems as we know it. I know that many of you in this class are biology majors, and organic chemistry is required for most biology majors, and the reason that organic chemistry is so important for biology is that it's actually the language of biology. The way that biological systems communicate to each other is often through organic molecules, the bonds being broken and formed, complexes of these organic molecules to send biological signals. So, why are you taking this class? Why are we here today, even if you're not a chemistry major? I know many of you will say, well, it's because it's required to my major. And I respect that, but I ask you to dive a little bit deeper into organic chemistry with me, because I know that there are many parts of this course which will be extremely important and useful for you no matter what career path you take, whether you end up working in some chemistry related field or some biology related field. There are many aspects of this class which are extremely useful and important for you to build your skill sets. If you're in a health science field and want to advance, OChem is the language of biology. So it's important for you to understand these interactions and how these molecules communicate with each other so that you'll be able to have a firm grasp of biology in the future. For example, if you're going to take biochemistry, a large amount of the information in organic chemistry is used as the foundation for the studies of biology. This can be compared to the relationship between math and physics, for example. In math, we learn how to manipulate equations, and in physics, we're using all of those skills that we learned in math to apply them to real-world functions. One of the aspects of organic chemistry that captured my interest early on is the amount of problem solving that this class requires. This class is much different than many classes because you can't really memorize your way through this class. Even if you have a photographic memory, there's a large amount of this class which involves solving and figuring out complex issues, taking concepts that you've learned and applying them to new systems. This skill set also develops your ability to do critical thinking. One of the comparisons that I like to make for the skills required to be successful in organic chemistry is to compare it to either a Sudoku problem or a critical thinking problem that involves taking different pieces of information, relating them to each other, and from that building a more full understanding of the system. And then finally, the most intrinsic aspect of this class is that by the end of it, if you if you're able to obtain a mastery or even a slight mastery of this class, you'll have the ability to manipulate and form chemical bonds that are responsible for life. And being able to do this with a certain set of mastery allows you to build very large and complex structures from small building blocks. And personally, I think that's pretty cool. And and that is what has led me to pursue a career in organic chemistry. So let's dive into content. Before we can build molecules, form new bonds, break bonds, we need to understand some of the basic properties of carbon, some of the basic properties of all of the elements that we're going to be working with, and we need to be able to communicate to each other the structures. We need to learn the organic chemistry alphabet. There are actually several different ways for us to draw organic molecules and to show these structures. The common way that you've learned in general chemistry is through the Lewis structure. The Lewis structure shows every single bond. These lines here are the chemical bonds. For example, this line is a representation or a model of the bond, the electrons that are shared between these two carbon molecules. We have lone pairs, which represent electrons that are local to a specific atom. We can condense the Lewis structure into the partially condensed Lewis structure, and what we see here is that the bonds between carbon and hydrogen are no longer drawn out explicitly. We're just assuming that those three hydrogens are bonded to this carbon. We also see that the bond between heteroatoms and the hydrogen is not drawn out, but it's condensed. So the partially condensed structure is going to be a more compact way of drawing out the molecule. We have the condensed structure. In the condensed structure, it's written out in a single line and no bonds are shown. In this case, we lose a little bit of the three-dimensional information, but it can kind of be implied through the condensed structure. And finally, we have the molecular formula. This gives you the least amount of information about the molecule. The molecular formula only shows you the specific elements and the ratio of those elements that are involved. So I believe all four of these methods of drawing organic molecules have been displayed or taught in general chemistry. In organic chemistry, we're going to add one additional method for drawing out molecules. Before we get to that point, please take a moment and write out the molecular formula for the following molecules. And I will add that there's going to be a worksheet attached to all of these videos, which will guide us through some of these problems. I'm not going to solve the problems in the YouTube videos, but simply explain the information necessary to solve the problems, and then we will work through these problems in the worksheet in class. However, I will attach the worksheet used to the videos for anyone that wants to practice these problems themselves. So in this question, I'm asking for you to convert the Lewis structure into the molecular formula for these molecules. Compounds with the same molecular formula but different structures are called constitutional isomers. So here we have three molecules. These are all different molecules. The connectivity of the molecule is different. For example, here we have an oxygen bonded to a carbon, and that carbon is bonded to two different carbons. That is isopropanol, or rubbing alcohol. This is the smell that you would be experiencing at the waiting room of a doctor's office. We have propanol. In this case, we have an oxygen bonded to a carbon, and this carbon is bonded to one other carbon and two hydrogens, whereas the oxygen bonded to this carbon is bonded to two carbons. We have ethyl methyl ether. This oxygen is bonded to two different carbons. So all three of these molecules are going to share the same molecular formula, C3H8O, but they're going to have different spatial arrangement, different connectivity. And we could see here all three contain 3 carbons, 1 oxygen, and 8 hydrogens. So these are constitutional isomers, compounds with the same molecular formula but different structures. Throughout the course, we're going to learn several different types of isomers, and this is the first one, constitutional isomers. So let's take a look at this molecule. This molecule is vitamin A, or retinol, and it's a fairly large structure. If you were to try to draw this on your sheet of paper that you're taking notes with, it would take you a fairly large amount of time to draw in all of those carbons and all the hydrogens. This is not the most efficient way to draw this molecule. How else can we draw this molecule or look at this molecule? We have the bond line formula. So the bond line formula, or the zigzag formula, is going to be an even more condensed way to draw out this molecule. Here we've replaced all carbons with specific endpoints or lines, and all of the hydrogens are implied except those that exist at the edges of the molecule. And we'll talk more about the bond line in a moment. Another representation is the 3D representation. This space-filling model shows carbons in black, hydrogens in white, and oxygens in red. This gives you a little bit more of a three-dimensional point of view of what the molecule would look like. And these bubbles are approximations for where the electron density is for around each of these atoms. So look how much easier it is to draw the zigzag formula than it is to draw, for example, the bond line formula or the Lewis structure. For the most part, we're going to use the line format. You are expected, though, to be able to convert back and forth between all 4 of these modes of drawing organic molecules for this course. However, this bond line structure will be primarily how we communicate organic molecules to each other. So let's start by figuring out how to read and generate bond line structures. Each corner or endpoint of a bond line structure is going to represent a carbon atom. So this molecule is hexanes. In hexanes, we have 6 carbons. And to begin with, this endpoint is the first carbon. And then each corner of the molecule, each time we see a turn in the line, we're going to have a carbon atom. So we have 1, 2, 3, 4, 5, 6 carbons. In 2-butene, we have 4 carbons. And you can see we have a double bond represented between carbons 2 and 3. One of the useful aspects of the zigzag format for representing these molecules is that it gives a fairly accurate depiction of the bond angles for the different atoms. So for example, between carbons 4 and 5 and 6, we'll have a bond angle of 109.5 degrees, whereas in 2-butyne, we're going to have an sp hybridized carbon, and that will have a bond angle of 180 degrees. So anytime we're drawing out a triple bond, it should be drawn out in a straight line compared to a single or double bond where we're showing a 120 degree angle or the implied 109.5 degree angle. We save a lot of time by not needing to draw in all of the implied hydrogens and also not having to draw in the carbon atoms themselves. Since the hydrogen atoms are going to be implied, we're going to have to create a set of rules to understand exactly how many hydrogen atoms are attached to each carbon or each other atom in the molecule. the drawing itself only indicates that there are two bonds connected to this carbon. We have one carbon-carbon bond here and one carbon-carbon bond here. But since carbon makes 4 bonds, we have to assume then that there are 2 hydrogens attached at that location. If we're to look at this carbon on the left here, this terminal carbon, we're going to have one carbon-carbon bond that's drawn in. And for carbon to make 4 bonds in this case, we'll assume that there are 3 hydrogen atoms at this location. So let's go through the rules of drawing bond line structures. The first rule is that sp2 and sp3 hybridized atoms in a straight line should be drawn in a zigzag format. So if we take this Lewis structure and convert it to the bond line, we can see that instead of the 4 carbons being in a straight line, we now have them in a zigzag. When drawing double bonds, we're going to draw all of the bonds as far apart as possible. So this molecule here, acetone, which you might be familiar with as nail polish remover, is going to have a 120-degree angle between the double bond and the single bond if it's drawn correctly. Here we have it drawn incorrectly, and you can see that this angle is only about 45 degrees. This is a much more accurate depiction of the proper bond angles for these atoms. When we're drawing single bonds, the direction in which we draw the bonds is irrelevant. We can rotate this bond here, for example, so that it's pointed in this direction, and these two will be the exact same molecule. When we're writing bond line structures, we can imply all of the carbon atoms, and we can imply all of the hydrogen atoms attached to the carbon atoms, but we must draw out heteroatoms and the hydrogens attached to heteroatoms. So anytime we have an alcohol, the functional group which contains an oxygen bound to a hydrogen, we must draw out both the oxygen and the hydrogen, as well as the lone pairs attached to the oxygen. And the cardinal rule, the most important rule, the rule that will help you to double check that your structures are correct, is that carbon is never bonded to more than 4 atoms. So never draw a carbon with 4 atoms, and this follows the octet rule. So let's take a moment and draw out all of the implied hydrogens for these molecules. How many carbons are found in each of these molecules? Also take a moment and draw the bond line formula for the following molecule. By the end of this chapter, you should be able to convert readily back and forth between the bond line formula and the Lewis structure. So in summary, there are several different ways to draw organic molecules. And we're going to be focusing on the bond line formulas or the zigzag formulas. Now I mentioned before carbon generally forms 4 bonds. This is because of the number of valence electrons. Carbon has 4 valence electrons, and therefore it's going to be able to form 4 bonds. That means carbon is tetravalent. Some of the other atoms that we're going to be focusing on and utilizing readily throughout organic chemistry are nitrogen, oxygen, and the halogens. Nitrogen is a trivalent atom. So every neutral nitrogen is generally going to form 3 bonds. Oxygen as a divalent atom is generally going to form 2 bonds. And the halogens as well as hydrogen are going to form 1 bond. One of the most common and infuriating mistakes to see made on exams or tests or any display of organic molecules is creating more than 4 bonds to carbon. And so this is often referred to as a Texas carbon, a carbon that makes 5 bonds. And that mimics the Texas state flag, the star that you see there. So at this point, the biggest takeaway that you really need to double check yourself on throughout the year is that carbon always makes 4 bonds. Please never draw a carbon with 5 bonds. It's going to be incorrect with whatever representation you're trying to draw. Okay, so here's a little practice problem for you. We have the molecular formula C4H10O, and take a moment and pause the video and try to draw out all of the constitutional isomers of C4H10O. How many different ways can we connect these molecules together? Here are the 7 constitutional isomers of C4H10O. You can see that each of them has a unique branching, a unique atom-to-atom connectivity of where the different atoms are attached to each other. Maybe somebody has come up with this as one of their potential examples, and this is incorrect because we're breaking one of the rules. Oxygen is divalent, neutral oxygen is divalent, so this oxygen is forming 3 bonds, and so it will not exist in its neutral form. So let's take a look at these 2 molecules. What is the relationship between these 2 compounds? To begin with, we can start by counting the atoms, right? We have 1 oxygen in both molecules. We have 5 carbons in both molecules. And we have 8 hydrogens in both molecules. The connectivity of these atoms in the 2 structures is different. So that makes these constitutional isomers from each other. We have the same molecular formula for both molecules, but we're going to have different atom-to-atom connectivity for the molecules. So these are not isotopes. They are not the same structure. They are not composed of different elements. The relationship is constitutional isomers. So I've been talking a lot about bonds, and let's take a step back and kind of go through what exactly is a bond. Atoms have valence electrons, or electrons that are surrounding their nucleus. And when the valence electrons from 2 different atoms join together, they're going to form a bond. So a covalent bond is a pair of electrons that are shared between 2 atoms. In this example, we're looking at a hydrogen-hydrogen bond. So 2 hydrogen atoms, each with 1 valence electron. Those 2 electrons bonding together to form a covalent bond, jointly associating the 2 atoms together. So this partnership is going to be what creates a chemical bond. There are several different forces in play that keep the bonds and the atoms associated together. We have an attractive force, and that attractive force is between the positively charged nuclei, and at the center of the molecule we have proton, we have the positively charged nucleus and protons at the center of the molecule, and on the outside of the molecule we have a cloud of electron density, which is negatively charged. So we have an attraction between the positive and negative forces, which pulls the 2 atoms together. At some distance, for hydrogen that's 0.74 angstroms, we have the most stable version of that molecule. The amount of energy is the lowest at this point. We want to minimize, for us to increase stability, we want to minimize the amount of energy that's present. If the molecules get too close together, right? So we have an attractive force pulling the molecules together. If the molecules get too close together, then we start to have a higher amount of energy or a less stable interaction. And this is due to the repulsive forces between the 2 positively charged nuclei. So the two centers of the molecule are getting too close together, and if you ever take two magnets that are north-south, both in the same direction, and try to push them together, you're going to feel that repulsion of the two positives pushing against each other, and that's a similar interaction that we see here. We also will see a repulsive force between the two clouds of electron density that surround the molecule on the outside of the molecule. So what that results in is a happy place, a happy medium of 0.74 angstroms, where the attractive forces and the repulsive forces are perfectly balanced so that we can create this chemical bond, and the atoms have a fairly standard distance between each other. So a review from general chemistry. When we look here at the periodic table, we have different groups, and the groups are going to give us information about each of these atoms. The largest piece of information that the groups give us, or the column that they're going to give us, is the number of valence electrons. The valence electrons are going to be the electrons that are found in the outermost shell of the atom. So at the center of the atom, we have positive charge, we have the nucleus, and on the outside of the atom, we have a cloud of electron density. The electrons can be found anywhere in that cloud, right? There's millions of electrons that are all surrounding each of these atoms in a sphere or some other shape, which we'll discuss more. And that negative charge is uh, kind of resonating around the atom in the middle. And depending on which group each atom is in, we have a specific number of valence electrons. And these valence electrons are going to be our focus, and they are going to be how we manipulate the unique qualities of each of these atoms, because they're going to have different a number of valence electrons, and these valence electrons are going to be our active players in chemical bonding. So for example, hydrogen is going to have one valence electron. Um, boron would have 3 valence electrons. Carbon, 4 valence electrons, and this is why carbon is going to be the um, most useful molecule when it comes to creating structures, because it has 4 valence electrons. It's able to accept 4 valence electrons from other atoms and therefore make 4 chemical bonds. And when we look at nitrogen and oxygen, we have 5 and 6 valence electrons. So this is I guess the kind of periodic table that you might be used to looking at. This is the one that I prefer. And this one is a little bit more indicative of how we're going to be, which atoms we're going to be working with in this course in organic chemistry. So we have in blue Du Bois, that's hydrogen, carbon, nitrogen, and oxygen. These are the 4 atoms that we're going to spend probably 95+% of our time working with in this class. These are the atoms whose properties you should know inside and out, especially as we go through the introduction to organic chemistry, because all of this information will be used directly as we're creating bonds and breaking bonds with these atoms in the future. We have the friends with benefits. These are highlighted in orange. These atoms are going to be used quite often in organic chemistry, and so we should have some idea of how they're going to interact. For example, the halogens are probably going to be the most frequently used, and they often will be part of the organic reactions that we're going to be studying. The rest of the periodic table, the transition elements, we're going to use them occasionally. Some of these weird neighbors will really scarcely use these, and then the mythical beasts probably won't be touching on at all. So let's take a moment and practice drawing some Lewis structures. This should be all review from general chemistry, but it's important to have a strong grasp of how to draw the Lewis structures. I'm going to go through the steps for drawing a Lewis structure, and then in the worksheet in class we're going to actually draw out these molecules and get some practice. So to begin with, you want to count the number of valence electrons each atom brings to the molecule, making sure to account for charge. And so I encourage you to practice some of these on your own. You know, we discussed nitrogen has 5 valence electrons, oxygen has 6 valence electrons. So that means we're going to have a total of, for example, here we would have 17 valence electrons. But we also have to account for charge, right? So the NO2 is 17 valence electrons. A positive charge indicates that there is actually a lack of an electron. So this NO2 plus molecule would have a total of 16 valence electrons. If we take NO2 minus, we would have a total of 18 because now we have an extra electron indicated here from the valence electrons of the 3 atoms. Then we'll draw a skeleton for the molecule, which connects all of these atoms using single bonds. The atom with the most available sites for bonding is going to be placed in the center. So carbon, we decided was tetravalent. Fluorine is a halogen that's monovalent, so we would put carbon in the center of the molecule. Then we're going to take the remaining electrons after we've written out the single bonds that connect the skeleton, and we're going to start filling in octets. Every atom should have 8 electrons around it, whether they come in the form of bonds or they come in the form of electron lone pairs. So we'll start with the most electronegative atom and fill in those octets. Once we've run out of electrons, right, we only have a number of valence electrons that we counted. If we run out of electrons, but we have not yet filled the octets, then we're going to start adding in double or triple bonds to make sure that we're able to fill all of these octets. And then finally, we want to make sure that the lowest formal charge is possible, and this will be something that we focus on in the first worksheet, is going through some of these examples and drawing Lewis structures. So here are some practice problems that you'll have the opportunity to get some repetition with. Throughout the slides and throughout the worksheets, there will be a large amount of practice problems available. Some of these practice problems you will see again. They will come in the form of test questions on the exams. So let's talk about assigning formal charge. And we hinted about it when we were drawing out the Lewis structures. Like I said before, we're going to be focusing on carbon, nitrogen, and oxygen. So I've prepared this table for you. There aren't many things that I will ask you to directly memorize. Instead, I would prefer you to focus on pattern recognition as we go through a lot of the content of this course. There are just so many things for you to memorize if you focus on memorization. But if you focus on recognizing the patterns and identifying the patterns, then you'll actually be able to create or come up with a lot of the concepts and knowledge on your own instead of relying on what you remember. And this formal charge table is a perfect example of that. So let's take a look at carbon. Carbon has 4 valence electrons. And here in its neutral form, we can see carbon is making 4 bonds and has 4 electrons around it, 4 valence electrons. So the formal charge here will be neutral. If we have 5 electrons, and when we're looking at the electrons that count towards formal charge, bonds count as 1, right? These bonds, carbon is sharing the electrons of this bond with another atom. So even though there are 2 electrons in this bond, when it comes to formal charge, carbon is only going to really get 1 of those counted towards it. If we look at this anionic form of carbon, we are actually going to have 5 electrons that count towards its formal charge. Each of these bonds has 1 electron that counts towards its formal charge because, like I said, the other electron is being shared with a different atom. However, now we have a lone pair on carbon. This carbon lone pair has 2 electrons, and carbon gets both of those electrons counting towards it with respect to formal charge. So this carbon is going to have 5 electrons around it, and since it has only 4 valence electrons, it's in group 4, right? That column on the periodic table, group 4. This is an anionic carbon. It has 1 more electron in its valence than the it's supposed to through its group. And so anionic carbon is always going to be making 3 bonds, but it has 5 electrons. Cationic carbon, now we have an empty orbital here with no electrons, so it only has 1, 2, 3 bonds, each of which it gets 1 electron from, and therefore it has a positive charge. So the formal charge of this carbon is going to be positive because it has 1 less electron than its group. Looking at nitrogen, we have nitrogen making 3 bonds and contains 1 lone pair, so 2 electrons. It's in group 5, so it has 5 valence electrons, and in its neutral form, it's also going to have 5 electrons, forming 3 bonds. If we look at anionic carbon, we're going to see an increased number of electrons around it. Instead of making a 3rd bond, we have 2 lone pairs on anionic carbon, and it's going to have a total of 6 electrons around it, 4 from lone pairs and 2 from bonds, 1 from each bond that it's making. If we look at a positive cationic nitrogen, we're going to have 4 bonds, each of which have 1 electron that count towards its formal charge, and so comparing that to its valence, it'll end up being net positive. And we can kind of look here at the trend, right? The number of bonds for nitrogen, neutral, it's making 3. Anionic, it's making 2 bonds. Cationic, it's making 4 bonds. So 1 less for anionic, 1 more for cationic. And this trend holds true with oxygen as well, right? If we have 7 electrons around oxygen, it's only going to be forming 1 bond compared to the neutral, which forms 2 bonds. And that will be anionic. So with regards to carbon, nitrogen, and oxygen, you can correctly draw all of these forms of the atom if you keep this table in mind. Look at and understand the trends, and notice at no point in time do we have a carbon making 5 bonds. So here are more opportunities for practice problems to draw out some more Lewis dot structures. So the next trend that I want for us to look at is electronegativity. Electronegativity is going to increase from left to right on the periodic table and from bottom to top. And I like to compare electronegativity to the greediness of the atom. How strongly is it pulling in electron density from its neighbors? How much electron density it's attracting. And so fluorine is going to be the most electronegative atom. And when we look at kind of the atoms here on the left, the electronegativity around 1, these atoms are going to have a much lower attraction for electron density than the molecules on the right side. So we look here, carbon, very balanced, kind of right in the middle here at 2.5. Comparing that to hydrogen, we have an electronegativity difference of 2.1. When we're looking at bonds, we're going to have three main different types of bonds. The first bond is a covalent bond. And in a covalent bond, we're going to share the electron density between the two atoms. These atoms are going to have a fairly similar electronegativity to each other. Uh, Anytime the electronegativity or the greediness or how strongly an atom is pulling electron density towards it, anytime that difference is less than 0.5, we have a covalent bond. These guys get along well. They learned to share, right? The carbons are going to share the electrons between them fairly equally. The carbon and hydrogen, the carbon's a little bit greedier, but there's still going to be a fairly large amount of overlap and sharing between the electrons found in this bond. Anytime we have atoms where the electronegativity difference is larger than 0.5 and less than 1.7, we're going to have a polar covalent bond. So, for example, looking at carbon and oxygen, right? Oxygen, we have 3.5, hydrogen at 2.1. So we have a 1.4 difference in electronegativity between the two. This is going to be a polar covalent bond, meaning the electrons of this bond are going to be hogged by the oxygen. Oxygen is going to pull more of the electron density to it compared to what carbon has, and so we're going to have a polar covalent bond. Anytime we have an electronegativity difference greater than 1.7, we're going to have an ionic bond. At this point, we're no longer sharing. We have one of the atoms really hogging all of the electron density, and that can be seen as gaining a full negative charge, meaning both of these two electrons are localized to that oxygen, and the sodium is more or less electron free, so it gains a positive charge. Electrons tend to shift away from lower electronegativity atoms to higher electronegativity atoms. Remember on the second slide I said we need to focus on the flow of electrons from negative to positive, and this is kind of an example of one of the building blocks of that we're going to be manipulating and probing as we develop our organic chemistry skill set. So if we look at carbon-carbon, these two atoms are sharing the electrons fairly well. When we look at carbon-oxygen, we have a much larger electronegativity difference. So the electron density in this is creating a polar bond, and oxygen actually has a partial negative charge. That's this delta, partial positive on the carbon, partial negative on the oxygen. We can think of the carbon as electron deficient or electron poor. We can think of the oxygen as electron rich. The oxygen is hogging those electrons. And for example, with lithium, we're going to have a polarity shift in the opposite direction. Lithium is much less electronegative than carbon, so we'll have here a carbon that can be thought of as having a negative charge on it, and the lithium is having a positive charge. And so the greater the electronegativity difference between the two atoms in question that are making the bond, the more polar the bond we have. And occasionally we'll have some examples where we can actually write them as a covalent bond or an ionic bond. Carbon-lithium is really right at kind of that 1.5 difference, so we can depict that as a carbon-lithium bond or a carbon-lithium covalent bond or a ionic pair between the carbon and the lithium. So take a moment and try to identify all of the covalent bonds for the following molecule. Sorry, all of the polar covalent bonds for the following molecule. When we're discussing the electrons that are surrounding a molecule, we need to formalize our models for where those electrons are. So remember that each of these molecules is made, and atoms have millions of electrons around them. The Lewis dot structure and the bond line structure are representations of where we suspect these electrons are, but they're not really very descriptive. They're kind of weak approximations. We can use atomic orbitals as models to get an even more accurate understanding of where exactly the electron density, where those clouds of electrons exist with relationship to the center of the atom, the nucleus of the atom. And so the this is actually a mathematical approximation from quantum mechanics. So the solution to these wave equations are going to give when you plot them, is going to give a atomic orbital. So this wave function gives an image of the atomic orbital, and these are mathematical estimates of where the clouds of electrons are around the atom. If you go into physical organic chemistry or physical chemistry, you'll go through some of the math of these approximations. But for now, we simply want to use this as a model to understand the shape of the areas where the electrons are going to exist for each of the different types of atoms that we're working with. So like a wave on a lake, an electron's wave function can have both a positive value and a negative value and a node. And so for each of the different orbitals, each different type of orbital, we're going to have a different type of shape. So for example, the 1s orbital is going to be a spherical shape. As we add more valence electrons, we'll need to add more orbitals, right? Each of these orbitals can only accommodate 2 electrons. So we have our 2s orbital, also a sphere. And then when we get to the carbon, nitrogen, oxygen, we're going to have p orbitals, 3 different p orbitals, which are more of these lobe shapes. So this is where we're able to visualize where the electron density is around the atoms. In general chemistry, you learned several different rules that we use to fill the atomic orbitals. And so we're just going to kind of summarize and go through those again, as well as fill out the molecular orbitals, fill out the atomic orbitals for our key players in organic chemistry. So the first principle, the Aufbau principle, is that the lowest energy orbital is filled first. Then, after that, each orbital is going to be filled with a maximum of 2 electrons that have opposite spin. So every orbital can accommodate a maximum of 2 electrons. And then we have Hund's rule. When you have orbitals that have equal energy, or degenerate orbitals, such as p orbitals, remember we saw that there's 3 p orbitals, x, y, and z. We're going to put 1 electron in each of those orbitals first before we add a second electron to any of the orbitals. So just looking at the most simple atom, hydrogen, we have 1 valence electron, and so that 1 valence electron will just go into the 1s orbital. So please take a moment, you could pause the video, and fill out the molecular orbitals for carbon, nitrogen, oxygen, and phosphorus. And here's what that looks like for the first row of atoms, right? Specifically, let's look here at carbon. Carbon is going to have 4 valence electrons, right? And we're going to have our 1s orbital that has 2 electrons, and then our 4 valence electrons will be in the 2s and the 2p orbital, and giving us a total of atomic number 6. So just another kind of depiction of what those orbitals might look like in 2 dimensions. We have our 1s orbital, we have our 2s orbital, both spheres, and then each of our p orbitals is going to be these kind of lobe-shaped orbitals. Notice that we have a positive lobe and a negative lobe for these orbitals, and that kind of goes back to that mathematical equation, that wave function where we have a positive and negative. When we're going to make a bond, we're going to have these two waves acting with each other. So if we have two atoms, as the atomic orbitals overlap and the atoms share the electron density with each other, the waves get closer together. We have two potential ways for this to occur. We have two orbitals that share the same sign, and when they become closer together, we get constructive interference. So as the two waves come close together, we have two positives, for example, creating constructive interference. If we have a negative lobe interacting with the positive lobe, then the waves will cancel each other out, and we'll get destructive interference as well as a node where we turn from positive to negative. So the bond of a hydrogen molecule, the bond of these two orbitals coming together, is going to result from constructive interference, or a direct overlap of the orbitals to form a sigma bond. So when the bonded electrons spend most of their time in the overlapping orbital space, we result in a sigma bond. When we transition between atomic orbital theory and molecular orbital theory, instead of thinking about the orbitals of an individual atom, we're going to start thinking about the orbitals of a more complex species, or the molecule, and the orbitals of these two atoms interacting together. So atomic orbitals are the wave functions that overlap to form the molecular orbitals of the entire molecule. So for example, let's look at hydrogen. With hydrogen, we have for H2, we have two hydrogen atoms, each of which bring one atomic orbital, one s orbital to the table. And when those two s orbitals get close together, and they form a bonding molecular orbital. This bonding molecular orbital is a combination of those two individual atomic orbitals. When we form bonds between molecules, we're going to have an equal number of molecular orbitals to the number of atomic orbitals that were present. So here we're going to have a bonding molecular orbital and an antibonding molecular orbital. Remember how I mentioned we have two potentials. We have constructive interference and we have destructive interference. Well, our bonding molecular orbital and our antibonding molecular orbital are going to represent those. So when the atomic orbitals overlap, the electrons are going to go into the bonding molecular orbital first. And this is because the bonding molecular orbital is going to have a lower amount of energy. If we go back and look at our wave functions here, we have a node in the destructive interference, and this is going to be a higher amount of energy compared to the constructive interference